Dear students, so welcome for the introduction of your lab 4. So in your lab 4, you are supposed to work with the analog to digital converter that's inherent in your silicon lab chip that you are using so far in your labs. So again, this ADC is a bit different than what you learned in the class, which is ADC 804 and 808 family. But this is a different ADC, so let me give you some introduction to this ADC chip, and then I will tell you what is the task that you have to do in the lab. So first of all, this is a ADC with 8 inputs. So you can see here, these are the 8 inputs, and this is a 12-bit ADC. So it converts one of the analog voltages here in one of the 8 inputs to a 12-bit digital logic, and it places the output into these registers, which is ADC0H and ADC0L. So the MSBs are stored in ADC0H and the LSBs are stored in ADC0L. This is called ADC0, by the way, and there are more ADCs in the Silicon Lab tool stick that you are using. We will be working with ADC0 in lab 4, so every registers has a name 0 associated with it, you see. So so now let's look into the details of the functioning of this ADC chip. So first of all, we have these special purpose registers, these 4 registers, which are called AMX0CF, AMX0SL, ADC0CF and ADC0CN. So depending on what combination of bits that you put here, the function of this ADC will change, or how you try to make it work. And then there is this ADC0EN bit, which actually controls this switch to switch on this ADC. So first thing you have to do is to set this bit to 1 so that this ADC is switched on. And then if you closely look into this ADC0CN special function register, you will see that there are 2 bits, ADC0CM1 and ADC0CM0. So based on the combination of these 2 bits, whether it is 00, whether it is 01, whether it is 10 or 11, these multiplexer will be selected. So see, this multiplexer is actually activated by the ADC0CM bits. So ADC0CM1 or ADC0CM0, that will activate this multiplexer, and based on the combination of these bits, the ADC will start conversion by one of these 4 methods. Okay, so again, we will be working with this particular method, which is which actually gets activated if you put ADC0CM equal to 0 and ADC0CM0 equal to 0. So these two, if you put 00, then this particular line will be selected, and if you put a 1 in ADC0BZ, this line, then the conversion will start. So so basically, this register, if you see this special function register ADC0CN, you have to put 00 here and 1 here to start the conversion. And I'm just right now skipping the other fields in this register, because we are not working with these modes. We are only working with the 00 mode, and 00 mode can be selected by putting ADC 0 CM1 equal to 0, ADC 0 CM0 equal to 0, and then you can start conversion by placing a 1 in this ADC 0 busy line. Okay, and of course you have to set this ADC 0 EN to 1 also to switch on the ADC or to power on the ADC. Now let's focus on the function of these three special function registers. So first of all, let's look into AMX0CF. So here you can see AMX0CF, the MSB 4 bits are not used. Only the LSB 4 bits are used, and based on the configuration of these bits, whether they are 0 or 1, the inputs here will be chosen as a single-ended input or differential input. So what does that mean? So you see AIN 0 and AIN 1, these are the two inputs here. Then again AIN 2 and 3, 4 and 5, 6 and 7. So let's say if you want to function AIN 0 and AIN 1 as a differential input, which means that you want to have AIN 0 minus AIN 1. So AIN 0 minus AIN 1, if you want to make the input as that, then you select this AIN 01 IC to 1. Similarly, if you set AIN 23 IC to 1, then the differential inputs will work for AIN 2 and AIN 3. So the input will be AIN 2 minus AIN 3. Similarly, if you put 1 here, then this is AIN 45 IC, so then that means AIN 4 minus AIN 5 will be the input, and so on. So but if you put zeros here, if you put 0 here in AIN 01 IC, then only the single-ended input will be chosen, only one of these. If you put a 0 here, AIN 2 will be chosen. If you put a 0 here, AIN 4 will be chosen. If you put a 0 here, AIN 6 will be chosen, and so on. So this AMX0CF, this register's function is to choose whether you are having a differential input voltage or a single-ended input voltage. So let me show you the details. As I said, so AMX0CF, which is the configuration register, the first 4 bits, the MSBs, are not used. These are unused, bits 7 to 4, and then from 0 to 3, this is the functions that I just told you. So if you put your bit 3 to 0, then AIN 6 and AIN 7 are independent single-ended inputs. If you put this to 1, AIN 6 and AIN 7 are respectively plus minus differential input pair. So it means if your bit 3 is 1, then as I said, the input will be AIN 6 minus AIN 7. If you put your bit 2 to 1, then it will be AIN 4 minus AIN 5. But if you put it to 0, then AIN 4 and AIN 5 are independent single-ended inputs. So this is how it works. So now let's see the function of this register, which is AMX0SL. So AMX0SL is basically again kind of a multiplexer. So based on the combination of these bits, you choose which of these inputs will be chosen. Input voltages will be chosen. So you see, this is again only the last 4 bits or LSBs are used, and these 4 bits can give you the inputs ADC chip. So so let's see. So this is AMX0SL, and if you see here that bit 7 to 4 they are unused, and then from bits 3 to 0 these are the address bits. So so basically if you put 0 0 0 0, you can actually put 0 0 0 0 to 1 1 1 1, and then it has different functions. But let's say if you want to choose the input 2 here, which you will be actually needing to choose in your lab, because there is a potentiometer which is on chip, and that is connected to your AIN2. All you need to do is to select 0 0 1 0. So that will give you the input pin 2 to be selected here, the input pin 2 to be selected, and that has a potentiometer connected with your ADC. And in your lab 4 you will be using that potentiometer and varying the input voltages by rotating that potentiometer, and then see the output of the ADC in the 4 LEDs that you have in your chip that you work with in the lab. So so there are more details to this AMX0SL. You can see it in the data sheet that you have. So for example, let me find it for you. So so here, so AMX0SL, you can actually have 16 combination, because you have 4 LSBs that are used, and based on that you have different modes of the input pins. So for example, your if you put 0 0 0, then everything is 0 here. But if you put 0 0 0 1, then you can see sorry, if you put 0 0 0 0, then everything is single-ended inputs. If you put 0 0 0 1, then you can see that you have a differential input, AIN0 and AIN1, and then if you put 0 0 1 0, then you have differential input here at AIN2, AIN3, and so on. So so depending on what you put here, and the bits at AMX AD30, you can choose the inputs. So sorry, AMX AD320, you can choose the input. So all you need in this lab is basically to choose the single-ended input AIN2. So for that you have to set the AMX0SL as, let's say, 0010. So you choose the AIN2, and then you have to put some values here, AMX0CF, so that you can only choose the single-ended input AIN2 and not the differential input here. So so these are the functions of these two registers. Now let's see the function of these registers, ADC0CF. So in the ADC0CF, basically there are two functions that can be configured by using this register. So bits 0 to 2, this bit 0 to 2 actually selects the gain of the amplifier. So if you have if you see this, there is an amplifier here, and the gain of this amplifier is selected by choosing the bits 0 to 2 of your ADC 0 CF special function register. So if you have 000 for these 3 bits, then you have the gain equal to 1. If you have 001, then the gain is 2, and so on. And then the rest of the bits 3 to 7 actually selects the clock. What is the rate of the input clock that you should set for the ADC? So you can see there are 1 2 3 4 5, there are 5 bits from ADC 0SC0 to ADC 0SC4, and whatever configuration you choose for these bits, the clock rate can be given by this equation. So this is your system clock, which is 22 roughly 22.1 megahertz for your Silicon Lab toolstick C8051F020 family. So that is 22.1 megahertz, and then this is the clock that you need, let's say CLK-SAR0. So this refers to the desired clock the ADC wants, and this one ADC 0SC is the bit combination from these ADC 0SC0 to ADC 0SC4. So let's say if I have ADC 0SC, this 5 bits equal to all zeros, let's say. So this side of the equation is 0. So 0, this minus 1 should be brought here. So 0 plus 1, this minus 1 comes this side and becomes plus 1. So 0 plus 1 is 1. So therefore it means that system clock divided by the clock that you are desiring, this ratio is 1, and therefore the ADC clock is equal to the system clock. So this means if you set these 5 bits to all 0, then you can make the ADC clock equal to the system clock. But then if you want to have, let's say you want to have a clock which is less than the system clock. Let's say you want to have a clock which is half of the system clock. So in that case you select these 5 bits as 0 0 0 1 0 1. So that means this side will be 1, and then 1, and then minus 1 goes here. So 1 plus 1, this minus 1 becomes plus 1, and 1 plus 1 becomes 2. So system clock divided by the ADC clock equals to 2 now, and therefore the ADC clock is system clock divided by 2. So in that way you can configure the clock by setting these 5 bits here. So this entire ADC 0 CF register, again to summarize, first of all it sets the clock, and also it sets the gain of the amplifier here, this amplifier. So you see, if you go back to the original figure, we have covered the functions of these 4 special function registers. So this one selects whether you want to have a single-ended input or a differential input based on this combination of bits. This one selects which of the inputs you are selecting, and also whether they will be single-ended or differential. And then this one, it actually gives you the clock rate as well as the gain of the amplifier. And these special function register, these 2 bits of the special function register ADC0CM0 and ADC0CM1 selects the start conversion mode. We focus on only 00 for these 2 fields because we will be working with only this input 00, and we have to set ADC0BZ equal to 1 to start the conversion. And then you have to also set this to 1 to start the ADC. These four registers have some different functions which we are not going to use in for this lab, so I'm skipping the details of this right now. If you are interested, you can check the detailed data sheet where everything is given. So basically these are actually doing some comparisons. Whatever the output of the ADC, digital output of the ADC, they are comparing that value with some values placed here. So if you place some values in the program you are writing here, it will compare these values whether it is less than the digital output or greater than the digital output. So these are the greater than registers. GT stands for greater than. So this will have 12 uh, sorry, this will have 6 bits, this will have 6 bits. So these 12 bits, whether these 12 bits are greater than these values, or no, sorry, this will have 12 bits, this will also have 12 bits, and here we have a combination of 12 bits. So they will be comparing whether these values are greater than these 12 bits or these values are less than the 12 bits. So you can check the details of these if you are interested, but in this lab you are not required to do this part. So basically in this lab what you have to do is, in your input 2 you have the potentiometer voltage, and if you change the voltage of the potentiometer by rotating the knob, then the ADC output will change, and the ADC outputs should be connected to the 4 LEDs that you have in your chip, and you have to see the change on the 4 LEDs by changing the inputs of the potentiometer. I mean changing the input of the ADC which is connected to the potentiometer. So that's what you have to do in the lab. Another important register you need to know and also need to configure for this lab. So that is the register called reference 0CN, which is the reference control register. So this register, you have to set the bits here equal to 1, these 2 bits, which is very important. So let's ignore these parts. For this particular case you have to set bit 1 equal to 1, which means the internal bias generator is on, and bit 0 to 1, which means the internal reference buffer is on. So this is very important, you have to do this. So if you set also actually you have to set these bits to 0 also, because let's see what are the function of these bits. So if you set bit 4 to 0, then basically you are selecting ADC 0 voltage reference from VREF 0 pin. If you set bit 3 to 0, then you are choosing ADC 1 voltage reference from VREF 1 pin. If you set bit 2 to 0, then you are actually switching off the internal temperature sensor. We are not working with the temperature sensor, so we don't need it. But bit 1 and bit 0 has to be 1 to switch on the internal bias generator and also to switch on the internal reference buffer. So this is the reference 0CN register which controls the reference voltages. The way it works is this. So if you have the reference 0CN fields activated accordingly, you can have these multiplexers selecting the reference voltages for the ADCs. So this one is for ADC 1 and this one is for ADC 0. We are working with ADC 0 in this lab. So this has to be 0, this AD0 VRS has to be 0, and then this has to be 0 also, because we are not interested, or actually this has to be 0 to set the ADC1, but we don't need ADC1 here. And then the temperatures has, this field has to be 0 because we are not selecting the temperature sensor, and these two has to be 1 so that the bias and the reference are properly set. So again, you can look into the details of this in your data sheet, but right now for the lab, what you need to make sure is that you select these fields of the reference 0CN register properly, and especially these two fields to 1 to set the internal bias generator on and the internal reference buffer on. And then finally, to make the ADC work properly, so these are the steps that you should follow. So when initiating the conversions by writing a 1 to ADC 0 BZ, so that's what we told before. We are writing a 1 in ADC 0 BZ and selecting the modes here, ADC 0 CM1 and ADC 0 CM0, so that this is 0 0. So this will start the conversion, and then once you start the conversion, you have to poll the ADC 0 int bit. Okay, so so you have to continuously poll this ADC 0 int bit to see whether your conversion has finished. So the first step is to write a 0 to ADC 0 int, and then write as 1 to ADC 0 BZ to start the conversion, and then you have to poll the ADC 0 int for 1. So you have to check the ADC 0 int bit, and when this is 1, then your data is ready to process in these two registers, and then you process the data. So that's the whole process. So these steps actually give you an idea of how to write the code to see whether your data is ready. So talking about the code, I have a file set up for you. So here you have to complete this code by doing some things here. So first thing is you set all these special function registers that I just discussed to their respective value. So you set AMX0CF, you have to find out the value X here, so that it makes all ADC multiplexer input single-ended and not differential. You have to select AMX0SL, this value Y. You have to find out the value Y to select the mux input number 2, that is AIN2, to which the potentiometer is connected. You have to select the value of ADC 0CF, this register, so that the gain is equal to 1 and the conversion clock is equal to the system clock. So you have to set the value Z accordingly. You have to move a number n to reference 0CN register to enable the bias generator and the internal reference buffer, which I just told, and then you turn on the ADC by setting this bit ADC 0EN. So this bit ADC 0EN to 1, and then this is the part of the code that will first start to poll the ADC 0 int pin that I just said. So this part of the code here, whatever you write here, will actually emulate these four steps. Write a 0 to ADC 0 in, write a 1 to ADC 0 busy, poll the ADC 0 int for 1, and then the data will be ready. So these four steps will go here. Actually here, so all of this. So first you poll the ADC int, you start the conversion, and then wait for the poll to finish, and the poll finishes when ADC 0 int is 1 again. So when this is 1, the poll finishes and your data is ready. So you have to read only the 4 MSBs, because your LEDs are connected to the 4 pins of the port 5. So you have to only read the 4 MSBs and shift up by 4 places, so that they are properly connected to the LED positions, and then you have to transfer them to the LEDs and then repeat this particular loop forever. So that's all about your lab 4 introduction. Go through this video and also go through the related sections in the data sheets here. So this is the data sheet that I have already given you at the start of the semester. So go through the related sections and try to understand what you have to do. Go through this video, and I will upload the blank code file, this one, and then you have to work on this code file to finish your lab 4 and show the outputs to me or the TAs in the lab. Thank you. Okay, so this is the output that you have to show in the lab. So if I change this potentiometer, these outputs are changing. So basically I am changing the input voltage, and the LEDs are changing because the digital output of the ADC are changing with the input voltage. So that's what you have to show as your final output.